Remember last time we were together, we did a real simple diagram. I hope that you have in your notes, but it doesn't hurt to think about it, that kind of like the movement of calculus. I can have a function. A function is a graph. I can do its derivative. We get f prime of x. We talked about that the first half of the year. We can go the other direction with an antiderivative. So yes, we can go back to where we started, but as we talked on Friday, we can also do the antiderivative and go one step further in that direction. And we get what's called capital F of x, which is also called the antiderivative. Okay, so it's kind of like we're going back in time, maybe. We watch Back to the Future. My kids never watch those before, so we had a good time watching them recently. But I don't know if this is really the same idea. It's just another movement with antiderivatives. Now, when you are asked to do an integral, we showed you this Friday, but I want to make sure you know what you saw. When you're asked to do an integral, remember, that's the same thing as, when you're asked to do an integral, you can subtract the antiderivatives. Note how you're subtracting them. It's always f of b minus f of a. I don't want you to think that it's backwards, but it's always the place I'm ending up minus the place I started. So it's f of b minus f of a, this value minus this value. Okay, and again, these are antiderivatives. I don't think I showed you that Friday. For some reason you want to write that down, you can. It's a changed function. Like, it's going to be a big oops if you don't hear this. You have to change the function. I'll be sure to do that every time. You don't just plug into the original function. You plug into the antiderivative. And also, I forgot, I didn't show you this on Friday, but remember, even though this is going to be new today, we're still finding the area. An integral is an area. So we kind of can use those two words interchangeably. So what that means is that f of b minus f of a, which is going to be the new catchphrase, f of b minus f of a, it's the same as the area. Okay. Now, think about the quiz you just took. You found the area using geometry. Okay. We're not throwing that out, but we're going to add to it how to find the area using integrals. All right. Are you ready? Okay. This is neat. You're ready for this? And let us begin with the integral of 2x from 0 to 4, but we want to find this using our new method, using antiderivatives. Okay, so the integral of 2x from 0 to 4. Now, I don't know if you realize this or not, we've only talked about antiderivatives a little bit. So if you're like, yeah, we haven't talked about them much, you're right. So we have to remember what we've done, and you're going to start to feel like that it's time to start thinking backwards. Okay. Now, there was something I showed you. It's called the reverse power rule. It's kind of your go-to method when you have a basic function. The reverse power rule said that whatever the exponent is, now, of course, it starts as 1, I can just add 1 and divide by the new exponent. That's called the reverse power rule. And it gives you the antiderivative. I think you can see that the 2's cancel, and we end up with an exponent of 2. So, oh, okay, x squared is the antiderivative. Okay, now according to this little formula, all I need to do is evaluate f of b and f of a. And I'm going to be showing that. I encourage you to do the same thing. Maybe you get to the point where you're sort of comfortable and you might not have to write it all down. But I just want to make sure you realize I'm plugging 4 into x squared. Obviously, that's 4x squared. Of course, it's 16. I'm also going to plug 0 in there. Of course, that comes out as 0. Now, what I do want you to show when you guys are doing these problems is these two numbers. And like I said, maybe you don't have to show plugging it in, but up here, we should definitely show, well, I should have said the subtraction of these two numbers. You definitely want to show the subtraction and, of course, the result. So we get 16. Now, I wouldn't expect you to have predicted that answer, but I wonder if you can make a connection about that answer. I wonder if you can make a geometry connection, like how we would have done this problem on the quiz. Well, let's take a look. You shouldn't be super surprised that we're going to graph 2x. We don't need a calculator for that. 2x is just going to be a slanted line. It has a slope of 2. And of course, we're graphing it, or we're looking at it from 0 to 4. So we can start to put some x values on our sketch. And this would have been a pretty easy problem for you a couple days ago. Be careful. Be careful. I need the y value here, indeed. But don't plug into the capital F of x. Make sure you plug back into the original function. So the function is 2x. Of course, that means the y value is 8. And I hope that you realize that the reason we're doing that is because we need the height and the base, because we need 1/2 base times height. 1/2, 4 times 8. And would you look at that? We end up with 16. We end up with 16. Now, maybe you're looking at that problem and you're saying, I kind of like doing it the old way. Okay, there's going to be a time where you can just do it however you want. Okay, but I do want you to look at this and say that obviously it's the same, particularly with our new antiderivative method. Now, antiderivatives can particularly come in handy when we start to have shapes that aren't just nice little triangles, nice little rectangles, even nice little circles. What if we have a shape that's that's some type of curved line. Now, parabola is always a good one to start with, but are you seeing where I'm going here? We're going to find the area. We're going to find the area that's connected to a parabola. Well, maybe it's good news. We don't need to graph it. We don't need a sketch. Actually, we just need an antiderivative. And you're going to find out that the antiderivative kind of can handle any function. Are you thinking about the antiderivative of 3x squared? Are you thinking about adding 1 and dividing by that new exponent? You don't have to show that stuff, okay? Sometimes you're just doing that in your head, but you need to do it. You need to show x cubed. You need to show that new antiderivative. We're on the second problem now. There's not as many of you, so the probability that somebody would notice this goes down, but there's something I'm wondering if you are wondering. I'm wondering if there's something you notice that maybe has been forgotten. I'm not moving on, so it's not something moving on. Antiderivative. You were the one that mentioned it the first time.
Yeah, we forgot the constant.
We forgot the constant. Let's talk about the constant. Okay, let's talk about it in this problem, and we'll have some good news for every problem. F of B. I don't want you to think like it's backwards. I'm purposely evaluating the second number first. F of A is the first number. That's the order that you do it in. Make sure you're plugging 2 into our x cubed function. So, of course, that's 2 cubed. Really, it's just the number 8. Now, negative 3 cubed. Okay, I would say that you should be able to do this without a calculator. There'll be a no calculator part of our upcoming test, but just do that carefully. Negative 3 times negative 3 times negative 3. Negative 27. Now, there was a plus c on this, though, right? All right, so let's stick it on, but I hope that it'll be the last time we do that. But let's stick it on. Why is it the last time that we're going to do that? Let's take our two answers and subtract them. Now, there's a couple things going on here. Definitely, we're always subtracting. It's f of b minus f of a. Subtraction signs we got to be careful about because you know that you're subtracting the whole quantity. Okay, so I subtract the whole quantity, and obviously we do a little distributive property. I know you know that, but sometimes that's the place where we make a mistake. So it looks like it's 8 plus 27, right? 8 plus 27. So what do you notice about your C's? What do you notice about your C's? Well, I hope you notice that this will always occur, that those C's would subtract out. Okay, it's going to happen every time because we're going to be subtracting every time. So if the C's are going to cancel out every time, we basically kind of turn a little bit and say we're not going to worry about that. You don't need to write down the plus C. It's not going to become part of our solution anyway. Okay, now that plus C will pop back up in the next chapter. It will pop back up in the next chapter, but it doesn't matter right now. What I'm about to show you becomes, I just know when we get to the end of this chapter and everything kind of gets put together, this becomes the number one mistake for kids. So I'm not just saying that, it really is the number one mistake. Why are we going to draw a sketch? I thought we couldn't use geometry. Okay, you're right, but there's something else I want you to see here. Now, notice I'm sketching the original function. Now, I don't think we need a calculator to draw a parabola. You know, the 3 is just going to stretch your parabola, so it's no big deal. Now, we're going from -3 to 2. We're going from -3 to 2. What I'm about to show you is the number one mistake with this. It's kind of an interesting problem because we end up with an area kind of on the left-hand side. Obviously, it's a shape that is not geometric. And then we end up with an area over here on the right-hand side. Okay, now the number one mistake that kids make with this new method, f of b minus f of a, is kind of like saying more than what it means. What do I mean, more than what it means? Well, the answer you get when you plugged in 2 was 8. The answer you got when you plugged in -3 was -27. Saying more than what it means is to say, oh, okay, that means that this area is -27. Oh, okay, that means this area is 8. But that's not what those numbers represent for multiple reasons. Okay? For one reason, I hope you just look visually over here and say, yeah, that wouldn't be negative. And you can't just do something silly like say it's positive. The point is that -27 is not the area of this region, nor is 8 the area of this region. But what they are two values that when they are subtracted, they give you the overall area. It's interesting. By themselves, they don't represent anything, not anything significant. Okay? But when subtracted, those two numbers represent your area. Now, if you're looking over here and saying, well, what about this one? Well, you know, where's the area of 0? Again, these two numbers by themselves do not represent something, but when subtracted, they give you the overall area. Okay, we'll be looking at that again. I just want to start putting that in your head. Don't overuse these two numbers, but do subtract them, and you will have yourselves a new method. Try one. Try the integral of 2t plus 2. Try the integral of 2t plus 2 from -4 to 2. And honestly, I'm kind of throwing in another variable just because the book likes to do that, and it's going to help you down the road. If you don't like the letter T, You could change it to X, but I encourage you to try to work with the letter T and get used to some other variables. I like that you're jumping in. You just might want to double check that your antiderivative is correct. There's a t squared, but then a 2t. Just let me know if you want to talk about that. I encourage you to plug in your numbers and see if you can take it the whole way. Now, if you're feeling like you got the right answer, can you confirm that answer with a sketch? We're going to make a sketch, so if you are just kind of sitting there and you want to do something, you can try to sketch this and go to the next step. The constant is just going to subtract out every time because you're going to end up subtracting every time. You're going to subtract f of b minus f of a. So you may just disregard the constant. You should be getting crazy 8s for both of these. Yes, that is correct. Check your math carefully. When you plug in 2, you get 8. And likewise, when you plug in -4, you get 8. I don't know if you kind of questioned what happened here, but it is correct that your final area is 0. We can get areas of 0. Let's investigate the sketch. Do you already see it? I see you guys on your calculator. That's fine. You can type it in your calculator. It's just going to be a diagonal line. It starts at 2 and has a slope of 2. Make sure that you realize why you get what you get. We did do a problem like this in the last section, but of course you would have watched it through just a video, so I didn't get a chance to really interact with you guys, but I tried to get you to realize that it's always going to be the area between the x-axis and the function. So we want to start to see that kind of area. I can tell that you guys are seeing it. And then over here, we have an area that continues on the other side. It's above the x-axis. Now remember, our final answer is 0. Our final answer is 0. Whether you did or didn't know that, we would still have to find some areas of these two triangles. This x-intercept, you may remember me saying in the last lesson, is important because it subdivides our interval. Okay, that's another important concept that's going to start to show up. So we subdivide and we find this x-intercept. It's an important number. Maybe you can just see it on your calculator, but technically an x-intercept is going to make your equation equal 0. That's why x equals -1 is the x-intercept. It makes the equation equal 0. Now, if you're like saying, Mr. Nair, why are you doing this with geometry? I thought we had a new method. I'm trying to make sure you guys understand what is going on and what's not going on. And it's important because soon you're going to start to mix methods. Before we mix methods, we need to realize what is and is not going on. Okay, we have a triangle. It has a base of 3. We have a triangle. It has a height of, well, what is the height of that thing? I believe it's -6. If you plug in -4 to your function, you can see that that comes out to be -6. So we have a triangle that has some dimensions. We should be finding the dimension of this triangle, but a little bit of inspection, we find out that it has the same dimensions. Okay, now maybe that doesn't surprise you, but I want to make sure we find the area of the first triangle so that you can see this. It comes out to be -9. So that's the area of the first triangle. And then we have the area of this triangle over here. We can call it maybe triangle 2, give it a little more labeling, but triangle 2, yes, it ends up with the same area. Well, sort of. Okay, actually, we want to realize that our two triangles, one of them, of course, has a negative area, and one of them has a positive area. But in the same manner, our overall area, the overall area, is still going to come out to be 0. Okay, which is obviously what we found a few minutes ago. Now, remember what I said back in this problem? There's a big mistake that kids make, and I'm trying to make sure that you see this so that we can move on. And the big mistake is that kids will overuse these numbers. I'll tell you, this problem is probably more of a sort of temptation. What do I mean, overuse these numbers? Well, to somehow think that this number is an area. It's not. This is the area. It's like so different. This number here is not the area of this triangle. Yeah, this is the area. Okay, but these two numbers, when put together, and you'll trust it, but when put together, they will give you the overall area. Okay. What do you think about this integral method? Do you trust it? Okay, it works. That's what I'm trying to show you. It works, but we have to realize what it says. It doesn't give us the individual areas. And if you're saying, I don't really need this sketch, right? No, yeah, right. You don't need that sketch to get your answer. But I just want to make sure you realize what it is. Now, let's look at some integrals that quite frankly, we're not going to sketch because we really don't have to. But they will use some antiderivatives that you might not realize that you know. Okay, so we're going to feel like we kind of upped the difficulty level a bit now. Here's a problem that might make you feel smart once we get it figured out. It's the integral of dx over the square root of 1 minus x squared from 0 to 1. Now, you see that written in the book. Well, probably what you're going to copy down onto your assignment would be the interpretation of this. So I want to make sure we realize that the interpretation of this is easily able to be 1 over the square root of 1 minus x squared. Okay, why didn't we write it that way the first time? Well, because I want to make sure you see the interpretation. So now what we're doing is we're trying to think about 1 over the square root of 1 minus x squared. Now, I don't know if you came to class kind of prepared to sort of call out the antiderivative for that, but there was a function in the first half of the year. There was a function whose derivative was this rule. It's a rule. It's an inverse trig function rule. And again, it's just honestly something that we have to remember.
Inverse tangent.
Well, you're close because that's one of the ones we studied. If it was inverse tangent, it would have just been 1 over 1 plus x squared. So again, you're close because it would have been a plus x squared. Take a guess on another inverse trig function. Inverse sine gets the call. Inverse sine. Now, if you're like, whoa, I must have been absent that day. I don't know if you're absent, but make sure you make the connection. The derivative of inverse sine is 1 over the square root of 1 minus x squared. So the antiderivative of this, the antiderivative goes back to inverse sine. Okay. All right. Well, once we have that antiderivative, we are free to plug in. We are free to plug in. You would be using a calculator. I would be remiss, though, to say that there's not a trigonometry thing going on here, but just being honest, for the scope of this class, I'm not requiring you to somehow know what the inverse sine of 1 is, but we could talk trigonometry if you wanted to. Stick around when the bell rings, we'll do that. But if you plug in 1, now I might say that you could, it might make your life easier if you recognize that number. 157 isn't just a random number. 157 is pi over 2. And sometimes you look in the solution manual and you see, oh, okay, they wrote it as pi over 2. Yeah, keep learning. Write it down as pi over 2. It'll help you recognize it. If you plug in 0, you get 0. You guys could plug that in. Okay, so we subtract f of b minus f of a, and we get pi over 2. Okay, I think I'm going to get cut off if I start another problem, but we have a few more to do, so come on back.